Hello, listeners, and welcome back to another episode of Cognitive Dissidence. As usual, I'm your host. I'm Jacob Shapiro. I'm also a partner and the director of geopolitical analysis at Cognitive Investments. Joining me on the podcast today is Myles Stapelberg. Myles is a graduate student at MIT in the Plasma Science and Fusion Center. In addition to that, he is a member of the Innovation Advisory Board at Cognitive Investments. This is not the place to unveil everything we've been working on in the background at CI, but I've alluded to this a couple times. One of the things we're working on right now is a new investment strategy that tries to use our expertise in geopolitics to understand and predict the behavior of different nations around technology. If you look at major technological advances like fertilizers or semiconductors or even space and orbital payloads and things like that, you can usually find geopolitics at the core. And when I say at the core, I mean it is one of the impetuses for governments and companies to work together to try and achieve some kind of scale or try and achieve these advances in technology. And you kind of hear that in some of what Myles is talking about. The fact that the US government is now interested in fusion is creating the swell of interest that actually makes the timeline for the advent of fusion much faster than I thought, at least based on what Myles was saying. There are three key innovation factors that we're looking at over the next 20 years: energy, living systems, and matter and materials. Obviously, the conversation I just had with Myles, and I'll be having more conversations with him, is about that energy plank. But you'll be seeing a rotating cast of our other Innovation Advisory Board members, hopefully coming on the podcast and explaining in real layman's terms what some of these concepts are that we are diving into very deeply, not just because it's interesting, and it is very interesting, but because we want to use this to allocate capital in a strategy that harnesses some of those technological changes and where geopolitics can help direct us to the forefront of those changes in general. I'll also just say this is where the pitfalls of being a generalist strike. A lot of geopolitical analysts out there, and I won't name any names, are guilty of being generalists, but by the fact that they know so much about so many different things, they think that they need to project confidence or they need to be experts about everything. I am not an expert on nuclear fusion. I will never be an expert on nuclear fusion, but I do know, using my geopolitical lens, that nuclear fusion and nuclear power in general is going to be a major issue here over the next 5 to 10 years. And so I know enough to know that I need to learn some things about nuclear fusion and about nuclear energy in general so I can understand at least what is at stake. And then I need to go out and reach out to people like Myles and do a lot of hard work and a lot of understanding to translate that both from an analysis perspective, from an investment perspective for our clients, and things like that. So we're going to have a whole podcast about the innovation strategy. We're going to be talking about it a lot more, but this is sort of a little peek behind the curtain to see what's going on. And Myles is a part of that. He's one of those folks that is in the background who's helping us generate that expertise that we need so that we can get the generalists focusing on where we think the money and the interest and the geopolitics is going to go, but where we also have that expertise so we understand it in a real way and we're not just spouting our mouths off because we have to seem like we know something about something. As you'll hear from the questions in this podcast, I really do. I come back to it all the time, that Socrates paraphrase: the beginning of wisdom is the admission that you don't have any. So in that spirit, I offer you this initial podcast into nuclear fusion. There will be a lot more about innovation, energy, living systems, matter and materials, and even just about fusion itself, because this was a very introductory and almost elementary conversation. So thank you to Myles. Thank you for listening. If any of that piques your interest, my email address is jacob@cognitive.investments. More than happy to talk to any of you about it if you want to hear more about it. So cheers. See you out there. All right, Myles, it's really good to have you here. You're the first person on CI's Innovation Advisory Board to come on the podcast. We're not going to talk about that now. I'm talking about that in the intro so people will know what that is. But it's a real pleasure to welcome you to the podcast.
Great. Thanks so much, Jacob. I'm more than happy to be here and excited to, have a little chat about fusion and what this means for the world.
Listeners, so before I came on, I was asking Myles kind of what his specialty was in nuclear science, nuclear engineering, and things like that. And he told me that he'd be able to give an informed layman's perspective. But if I asked him to give a probability distribution function for electrons in plasma, he wouldn't be able to do that. I don't know what those words mean strung together. So, and I don't think there are any plasma physicists listening to the conversation, Myles. So I think you're automatically the smartest person in the room about the topic we're about to discuss, which is nuclear fusion. And I wanted to have you on since the really the U.S. government made a big deal about this, I guess, discovery or achievement in sort of the quest towards nuclear fusion. So I'm going to ask I'm going to take advantage of being sort of the dumber guy in the conversation, ask some really basic questions to light the way for our listeners, and then maybe we'll get a little bit deeper as we get in. But I want to start before we even get to what the Biden administration was touting and what happened in December. What is nuclear fusion? Why is it so important? Why has it been the holy grail of nuclear research for since the 1970s, or maybe it's been longer? You tell me. But what is nuclear fusion, and why are people so obsessed with it?
Yeah, so I think to give some perspective, nuclear fusion is the process that our sun and suns all over the universe use to produce, or let's not make, but generate energy. And the process is the complete opposite of fission, which is what people think of when they hear nuclear, the splitting of uranium. Fusion is the combination of two very light elements. And so on Earth and in the sun, we combine hydrogen, although it's not the standard hydrogen you see in water, or not intentionally, or like hydrogen in gas or any other like normal area of where you would see hydrogen. But we use specific types or isotopes of hydrogen. And the easiest way to have fusion is to use one isotope that has a proton and a neutron, and that's called deuterium. Normal hydrogen just has a proton in the nucleus. And so you get one of these deuterium atoms that has a proton and a neutron inside of the nucleus. And then you get a more specialized version or isotope of hydrogen, and that's called tritium. And what tritium has, it's got a proton and two neutrons. And so in total, what we're doing is we're taking two hydrogen atoms, one proton in each of them, but they have different numbers of neutrons. Slam those together, and when you slam those together, that's the hard part, you make helium. And helium is one of the most stable elements we have. It's got the highest, or it's incredibly stable. So from an energetic standpoint, we love to make more helium because it's stable. And so the energy that you sort of get from making that helium atom is released. And so you get a ton of energy released when you make helium. And that energy is released in the extra neutron because a helium atom has two protons, two neutrons. But remember, before we combined the two hydrogens, we had a proton in each of them, so two protons. Mm-hmm. But in one atom, we had one neutron, and in the other atom, tritium, we had two neutrons. And so the helium atom has two protons and two neutrons. So there's an extra neutron there. That's where most of the energy from the fusion reaction is concentrated. And you can get this through conservation of momentum to figure out exactly how much energy is attributed to the neutron. But for the easiest fusion reaction that we're worrying about, and the one that NIF used to break this new record, we were combining deuterium and tritium to make a helium atom and a neutron. And let's say we make an actual fusion reactor, the way we're going to harness the energy created from or generated from the reaction is by slowing down that neutron, which is similar to what we do now in fission, but we're going to slow down that neutron. And as the neutron slows down, it's going to deposit its energy into things. And so it's going to heat stuff up. And so we're just going to heat up a fluid using a fusion reaction. And that's sort of what fusion is and how we're going to try to harness that energy to do things like generate electricity, make new fuels, make heat, or not make heat, but like generate heat. There's a whole list of applications that one can work with when they have the finished, or let's say the harvested energy from the reaction. So I guess to summarize, because I know I said a lot of mumbo jumbo there, we're taking two hydrogen atoms that don't want to get together, but we'll squeeze them together. And then they form a more stable atom. And so the difference, because it's more stable, there's excess energy or mass that's converted to energy. via E equals mc squared, and a neutron that's left over from the reaction, and we get the energy from that neutron. And so this is sort of the thought process. All we're doing is we're combining two atoms together, making a new one and a spare particle, and taking the energy that comes from that extra particle. And I mean, this is a more of a specific version of fusion. You can do fusion with any other type of element. It's just the easiest with deuterium, which is the proton and the neutron hydrogen, and tritium, which is the proton and two neutron hydrogen. And so the reason why I use that example is because that's the one that we as fusioneers are going to actually use in the first design of a power plant, because all the other ones are so much more difficult, and it's already hard enough to it took 60 years for us to get more power out than we put in just with the easiest fuel, the DT reaction. So
Yeah,
that's sort of like my spiel on what fusion is from a basic standpoint. Was there like any clarifications or ways that I perhaps didn't explain it as clear as a more practiced individual would have?
No, we're off to a good start, and I love I love that you are a self-described fusioneer. But I guess my first question after that is, what makes fusion so special? So why don't we just keep on doing things with fission? Is it that fusion is more efficient? Does it create lots more energy? Why is fusion so important, or why is it so different than fission? Why aren't we spending our time perfecting what we already know how to do versus this thing that seems to be really complex?
Yeah, that's a great question, because I think the main allure of fusion is the plentiful fuel to use it. I mean, it uses hydrogen, which is really common everywhere. It also needs lithium, which is going to be a bit more contested, but we have enough lithium going around to keep fusion on the ground for now. And I believe the last number was like 1,000 years or so, based on the U.S. geological surveys. And I would say like the zeroth order reason why fusion is attractive is, I think there's like for every fission like reaction, we get about 200 MeV, which is a unit of energy, a mega electron volt released. Now, for fusion, we get 14 MeV. 14.1 technically of harvested energy, because there's really 17, but part of that stays in the plasma, and it's not as easy to extract. But we get it's like for every fusion reaction, we have way more of those than fission ones, and so and fission, much bigger atoms. So if you take that per atom, you get around, I think it's like an order of magnitude or so of more power from fusion than you get from fission if you hold up everything else constant. These are more order of magnitude estimates, so you get more energy out per sort of specific amount of fuel.
Did I mishear that? I thought you said 200 MeV for fission and 14.1 for fusion. Am I missing something?
So fusion, though, the atomic number, it's like 238 or 235, and you're splitting that. And it's a much heavier fuel. So if you normalize it by the number of atoms involved, then fusion jumps up by an order of magnitude, because you're dealing with 5, say, nucleons. So if you do like, what is it, 14 point, if we're going to be really proper, it's 17.6 divided by 5, and that's around, let's just say 3.5. And these are just sort of, I like to joke with people. They think I do like a lot of calculus and all that stuff. Most of the math I do is just dimensional analysis. The real smart people do the hard math. And if you do 200 divided by 239, so you're getting around 4 to maybe 7, depending on the spread of energy, times more energy. You get 4 to 7 times more energy from fusion per atom than fission. So for a gram of each fuel, you're getting like way more energy out from doing fusion. And I might be a little bit off, but that's the sentiment there. That's sort of the inclination of how much power you get out, and
No,
that's
no.
one of the reasons.
That makes sense. But then, so probably what is probably another kindergarten question for you is, because I mean, 238, I assume that's uranium that you're referring to. So we're splitting uranium when we're doing fission. Why, like,
Yeah.
if we were splitting helium, would we be getting similar level? Like, why aren't we splitting like things like helium or hydrogen? Is that also just not going to give us the energy we need, or why are we on uranium or plutonium or whatever it is?
That is, yeah. So this is one of the first things they teach us in applied nuclear physics, and this is the concept of binding energy, and it's related to Einstein's E equals mc squared equation. And so the binding energy is sort of the amount of energy required to keep that atom together. Binding energy, that kind of makes sense. And so you can divide that binding energy by the number of nucleons in that. And nucleons are protons or neutrons. And so you divide the total binding energy by the number of nucleons it has. And you'll see that the material or element with the highest binding energy per nucleon is iron 56. So it is the most stable material that we know of, and that's one of the reasons why we see a ton of iron. It's the most abundant sort of metal in our Earth, at least one of the reasons why. And so the reason why I bring that up is elements or isotopes below iron are much more likely to undergo fusion. It's much easier for fusion to happen there, and that's the reason why you start to get into the quantum physics, which is not something I'm most confident or comfortable talking about. But the sort of rule of thumb is, if it's lighter than iron 56, it's easier to undergo fusion. If it's heavier than iron 56, it's easier to split apart. And we quantify this by doing this thing called a cross section, which is really an areal probability. So it's like, what is the probability of my fist hitting my hand? This is a very linear, let's say, simplistic approach. But you could think of, like, the bigger my hand gets, the easier it is for my fist to hit it, kind of. Now, there's the other reason why this analogy doesn't hold up is my fist would have to be really a collection of atoms, because there's this, my entire hand is like 100% there, pretty much, like ignoring quantum effects. At the atomic scale, your atoms are moving all over the place, and so there's different probabilities for interactions to occur. And I think the easiest way to think about this is, in fission, you've got a giant target of uranium and a neutron. It's very likely for that neutron to hit the uranium, but depending on the uranium, type of uranium, so the isotope, so 235, for example, it's actually due to the pairing. So the number of protons versus the number of neutrons that dictates the ease of fission. Because there's some isotopes of uranium-238 that are much harder to split apart. And so depending on the energy of the neutron going in and the number of protons and neutrons, that dictates how easy it is to fission. Now, if we're on the fusion side, we also care about the number of protons and neutrons in the fuel. But it's more so when you fuse them together, what is the product that I create? How stable is the product I create? The reason why deuterium and tritium are great fuels comparatively when used together is that they form helium-4, which is one of the most stable. It's up there with iron 56 in terms of its binding energy per nucleon. It's got a really high binding energy. It's really stable. It doesn't want to split apart. And so because we can make that using deuterium and tritium, we like to do that with fusion. Now, it's still really hard. The reason why is because hydrogen is it's got one proton in it, right? And if you ignore the electrons, which is kind of what we're doing in a plasma because they separate, we're trying to put two positive things together. If you get two magnets and you put the pluses together, there's a push, right?
Mm-hmm.
So if you try to overcome that push, you can do it with magnets on Earth, right? Like just kind of make them touch. It's way harder to do that with hydrogen, and that's called Coulombic repulsion. And so the way to overcome this Coulombic barrier is you kind of smash them hard enough at high temperatures for long enough times, and then eventually they fuse. And so there's a few ways to do it, and the way that NIF did it, the National Ignition Facility, is they just had more lasers, and like they were basically playing like the evil Bond villain, and that their solution. I'm simplifying their great scientific work a bit, but like they were in part able to do this because they had the biggest, baddest laser, and it's really awesome. Like what they did is, if you want to get into how NIF worked, and I can compare this to how more, let's say, commercial facing designs are operating. But let's start with NIF because this thing was incredible. They've got like their peak output of power is 400 terawatts, I think, for their lasers. To give perspective, those green lasers that we use that we're not supposed to point in people's eyes are like a couple hundred milliwatts, maybe. Like I think like a 50 milliwatt laser is pretty hardcore. Like the 1 watt laser, the giant blue one, can pop popcorn and burn your skin. So they've got 192 lasers pointing at a fuel the size of a BB. And they hold this fuel in like this little complicated container that's gold coated, and they call it like a holram or something like that. A holram, and I don't know. I'm not a plasma physicist, so for those who are, please correct me on how to pronounce it. Regardless, what it does is all those lasers go into the holram, and those lasers bounce around until they converge onto the fuel pellet. And what happens is the fuel pellet gets hit by a ton of lasers all over it. And that creates a huge amount of heat on the surface of the fuel. And that heat increases the temperature, and you have this cold fuel in the middle, hot on the outside. And so the hot on the outside compresses. And so you get this rapid heating and rapid compression. And that allows you to overcome the Coulombic barrier that's preventing the hydrogen atoms from fusing. So by using a ton of lasers, we can squeeze the heck out of that fuel and encourage some of the atoms in that fuel to fuse. And that's what they did.
There's something like really poetically beautiful about the idea that forcing things together creates more energy than splitting them apart. I don't know. I'm just struck by that. But so my next question for you is kind of gets more to the how, which is because I saw that China didn't want to be caught flat-footed here because they announced, I guess, in the last week, some fusion breakthrough based on what was it exactly? They're doing some project. I just had it in front of me. But the gist of it was that they're using magnets, not lasers. So I wanted to ask, I assume that, or not that I assume, it seems to me that there's lasers and there's magnets, and those are the two ways that you can do fusion. Is there another one that I'm missing? And what is sort of the difference between using magnetic fields versus using lasers from kind of your perspective? Is lasers the way to go? Is it just, 6 to 1, half a dozen to the other? Are magnets less technologically advanced? Like, how do we benchmark kind of where we are with the lasers versus magnets thing?
Yeah, so that's a great segue to the next point, right? Because I think if the short answer is it's much, much more likely that the first commercial fusion power plant we see is going to be a magnetically confined fusion reactor. So something more similar to what East was. And what East demonstrated recently, to my knowledge, is a record for sustaining a certain temperature for a longer period of time. So if we go back to that Coulombic repulsion thing, right? There are three things you need to do to overcome that barrier. One, you need to squeeze the atoms hard enough. The sun does this by being just giant and having a huge gravitational force behind the fuel. The second thing is you need it to be very hot, because the hotter your plasma is, the more energy is in the system, the more vibrations the atoms get, which increases the number of opportunities you have for the atoms to hit each other and fuse. So, and that also scales with how hard you squeeze. So it's a combination of how hard you squeeze, how hot it is, so how many times they oscillate. And then the third thing is the confinement time. That is basically how long it takes before your energy starts to leave the plasma. And so you want a very high confinement time. And I'll get into this a bit more when I compare ITER to some of the smaller, newer designs, that particularly the ones that came out of MIT. But let's first talk a little bit about, this EAST was another really cool thing, is that they showed that they could sustain a temperature for a long period of time. And they had this new type of confinement, which this is into the plasma physics, and I don't think it's that appropriate for me to explain it. But it's a big deal, but I think the biggest deal would definitely be the recent NIF experiment, because this is sort of how I see it. For the past 60 years, every single experiment that we've done for fusion has been like making sparks with flint and steel and looking at those sparks to try to guess what a fire is like. And for the first time at NIF, we made a fire. Even though it lasted for nanoseconds, we made a real fire. And so even though we'll probably not use the laser inertial confined fusion for generating electricity for the grid or doing all these other crazy things that we can do with fusion that are great, we can learn a lot from that experiment and the subsequent experiments that'll happen there, so that we can better design the more commercially viable alternatives to achieve fusion. And so I think that's sort of the real importance there. And what the EAST reactor just showed is that we can get to the temperatures we need for the times required using the magnetically confined reactor. And the final piece to that puzzle is something that MIT and Commonwealth Fusion Systems have already solved. They solved how do we squeeze the plasma hard enough. And they did that by taking advantage of newer superconductors. So I don't know if you've heard of these high temperature superconductor magnets. People said we were going to use these to make maglev trains, and that we would be using maglev trains all over the place. I mean, the economics of maglev are another talk, but what's great about these new magnets is you can get roughly double the magnetic field strength compared to older magnets. And in a tokamak, the amount of power you can generate from the reaction scales with the strength of the magnetic field to the fourth power. So if you double the strength, it's a 16x increase in power. It's pretty huge. And so the closest we had ever gotten to breaking even with a magnetic tokamak, or with a tokamak, because that tokamak is magnetic. It's a magnetically confined reaction in Russian. That's the abbreviation tokamak. But by being able to, before having these gray magnets, we got to 0.6. If you divide the energy in or energy out by the energy in. And so multiply that by 16, we're getting somewhere, that's like almost 10. And ideally what we want is around a Q of 15 or 20.
This also might be a very sort of basic question for you. It might even sound ridiculous, but I'm wondering if it's related to the supermagnets, which is what, like, once we, like, let's say we start a fusion reaction, we've got a reactor, everything's going great. Like, what's to stop the reaction from just like consuming everything? Like, are we in danger of like creating a star in a reactor somewhere and swallowing the Earth with like a reaction that we can't control? Or is that like, I'm like, the science is not like that, and I'm thinking like a science fiction movie fan?
Oh, that's a really good question. So like, let me first give an example of fission. A poor designed fission reactor is like a really pissed off bull. If you don't have a steady grip on it, it's going to rampage out of control. And that's what happened with Chernobyl. A poorly designed fusion reactor is like a car with the wrong fuel. Or like it's you're not even going to get it to start up. Like yeah, like it's so difficult to get the temperature and the pressure configurations, and the higher you heat up this is actually what almost killed the fusion program. But the more you heat up, the higher temperature the plasma gets, the more you have to heat it up. It's a non-linear increase in the amount of power required to initially heat up the plasma. We thought it was going to be semi-linear, but it turns out it goes not exponential, but it goes from like linear to maybe quadratic or even worse. And so one of the benefits of fusion is it's so hard to sustain that reaction that in a disruption, an accident, you're not going to go get, the worst thing that can happen is a containment leak, which is serious, but it's like, and some part of the work of my research is in mitigating disruptions and designing materials and vessels to handle that disaster event. But what happens in a disruption, and this can be started really easily, like let's say you have your reactor. Normally, if this was on Zoom, my Zoom background is a tokamak, so I can like point to the thingy here. But like a fusion reactor, the interior that surrounds the plasma, it's shaped like a hollow donut. And that's a torus. And so on the inside of that torus, there's these little tiles made of tungsten. And we're coming up with other ideas, but right now, that's tungsten. If a piece of tungsten, the size of a pencil lead on the tip of a pencil, that sort of small little piece, if that falls into the plasma, your temperature is going to drop and your resistivity is going to increase by more than 10 orders of magnitude. And so all of the current, like the charge, all like the juice that we were pumping into that plasma, it no longer wants to be in the plasma. Because before, the plasma was a really good place for the electricity to sort of spin around and like do its thing. We were like making the fusion power. It was great. But now it's a resistive mess. It's like running through a swamp. And so it leaves the plasma and goes into the next most conductive thing, which is going to be the structural components. And it will rip apart the structural components, because when a current interacts with a magnetic field, you produce a force. It's called a Lorentz force. They're terrible, and it's electromagnetism stuff that I never was really good at. The first order thing to think about here, though, is disruptions are bad. They designed a giant vessel at JET in the UK to handle disruptions, and they still had a bad disruption, and it lifted tons of steel and concrete a centimeter upwards. And these things had bolts the size of me, and I'm like 5'10" or so, like my size. Bolting, they had, I believe, like almost, I think, close to like 30 or maybe a few more, but using those to bolt down the reactor, and they still lifted the reactor up because it was so strong. So disruptions are bad, but the worst case scenario for a disruption is you break containment, and at that point you are more worried about releasing like radioactive dust. But the good thing is most of this dust would be heavy, because it's likely going to be tungsten. And the half-lives are not too long on that. So you can, it's a lot, but it's not going to be a really explosive thing. It's just going to be like crumpling an aluminum can, and then it would be much more easy to contain, let's just say. And that's the real key takeaway here is it's hard enough to sustain a fusion reaction. It's not going to go super critical like with Chernobyl. And it's much more easier to design containment for that. And we're actually in the process of designing disruption-resistant vessels, like vessels that are designed to handle tons of disruptions. And so there's likely, before you're even going to have fusion on the grid, advanced disruption-resistant vessels already out there. Because right now, the way we do it is just use a ton of steel. And it's not the most efficient way to do that. But.
Well, so I think that's a good segue then into getting a little more specific, which is, so what happened? Like what happened that these scientists did that represented a breakthrough? My like layman's understanding is it takes a lot of energy to do fusion, and for the first time they were able to get more energy out than they were putting in. But that seems relatively basic. So why was this such a big breakthrough is the first question.
I think you hit it right on the head. It's a really basic but important breakthrough. So there's a few ways to define energy in or energy out over energy in. But if you look at just the energy coming from the lasers into the fuel, they measured about 2.05 megajoules. Yeah, so 2.05 megajoules of energy into the plasma or into the fuel. And when it generated a plasma and released energy out in the form of neutrons and X-rays, they got 3.15 megajoules out. And so if you divide that, you get 1.536 times the energy out versus the energy in. It changes when you start to look at the power or the energy required if you look at the wall outlet. This is sort of the Q engineering that we call it. And this is really what's important for a commercial plant, the Q engineering. You ideally want a plant that has a Q engineering of above 10. 20 would be perfect. And those are, like, if you could hit those numbers, then that's going to be a really economic plant. What engineering considers is all the systems, the energy required to keep those running. It took 300 megajoules roughly, according to the press conference, to fire up all those lasers and get that 2.05 megajoules into the plasma. So if you look at the wall, it's about a Q of 0.01.
What is 300 megajoules? Help me imagine what that what would that power or.
So 300 megajoules is an amount of energy. Let's see. So 1 Tesla battery, I think, is around let's just say they're like 100 kilowatt hour.
Mm-hmm.
So let me pull up. My best friend is Wolfram Alpha. So if I divide 300 megajoules by 100 kilowatt hour, that's about 83 or so Tesla batteries built up.
So by that definition, it seems, and you said they only got 2 joules out of it, or something like a little over 2 joules. So they
got 3 megajoules.
Oh, okay.
Yeah. So that's So 1 kilowatt hour is around 3.6 megajoules.
Mm-hmm.
And a kilowatt hour is basically the amount of energy you generate by having 1 kilowatt of power. So power is the energy per second in watts. And so a kilowatt hour is 1 kilowatt times 1 hour. So 3,600 seconds. And so it's about 3.6 megajoules per kilowatt hour. And so if you look at it, if we look at it in Tesla batteries, roughly, This is a fun unit. So 100 kilowatt hours, 1 Tesla battery, is about the amount of energy we needed to get the energy into the plasma. So if you look at the wall, we would have about a Tesla amount of battery would have been there. So it's a lot of energy still.
So we put in 1 Tesla battery and we got out roughly 1 Tesla battery.
We got a hundredth of a Tesla battery.
We put in 1 Tesla battery and we got out 1/100th of a Tesla battery. So
Yeah.
Well, so I don't understand what the leap was. I thought that we put in. I thought we got out more than we put in. So I guess like it's depending what you define as energy. Was that sort of the point you were making at the beginning of the answer to your question?
Yeah. So the point I'm trying to make is, and this is arguably the more important point. If you look at the Q science, the scientific ratio of the energy out versus the energy in, that only considers the energy directly going into the fuel.
Mm-hmm.
Whereas if you look at the Q engineering, which is more for the commercial aspects, but we're not commercially viable, we're not commercially ready yet. We care right now a bit more about the science so that we can fund the necessary work to get the reactors on the grid in about 15 years, 10 years. It's looking closer to 10 right now. In that case, no one in the world has ever even done a Q science above 1. If you're explicitly looking at the energy in versus the energy out of the plasma. Now, inertial confinement can get Q science above 1, but its Q engineering is a lot lower. So that the Q engineering is the 1 Tesla in, 100th of a Tesla battery out. Tokamaks have a bit better scaling in the Q engineering, but we haven't gotten a Q science good enough. However, with these new magnets that Commonwealth Fusion Systems has demonstrated, we're already in that ballpark. They still have to build the prototype, and that's what they're doing right now to verify that they can do it with a tokamak. But the recent breakthrough was a huge scientific breakthrough, and it has done more for fusion already than countless of other experiments because it's increased the visibility of fusion. And now there's a ton of excitement and encouragement from the government and from all these private startups that are trying to do fusion to, put the pedal to the metal and work on the problem. And that, I think, is the inherent true value of NIF. And I think that's why it's so incredible to have them at the National Ignition Facility pull this through. And it wasn't just them. There was people at MIT, Princeton, I believe Columbia, UCLA, UCSC, like all over the U.S. and also all over the world working on this problem. So it was a great collective effort for the fusion community. But does it really affect the needle on when we bring in commercial fusion? Not directly, but it generates a ton of interest and a lot more funding so that we can do that.
Is what they did in this breakthrough, is it scalable? Like, because you sort of anticipated what was going to be sort of my final question to ask you before I let you go, which is like, what is the timeline here? When are we going to see a fusion reactor? I was going to ask, is it in my lifetime? I think you threw out a decade, 15 years kind of out there. So that suggests to me that whatever they did is something that is scalable in the short term, and that it's realistic to think that we can be there in a decade or 15 years time. So help me benchmark sort of like, because it's great that there's visibility and stuff like that, but if you have to move heaven and earth just to get a Tesla battery worth of power, like that's probably not going to work. So is there something in what they did that allows us to see that we can scale? And what is the time horizon, you think, from your perspective on fusion reactors being something that actually generate power in our world?
Yeah, so I think the short answer, the technology demonstrated at the National Ignition Facility was not designed for power generation. That is a science experiment that we needed originally to simulate the environments of nuclear thermonuclear weapons. So the biggest nuclear weapons, stuff that came after Hiroshima and Nagasaki, are actually a fusion fission hybrid. And so it's a combination. It uses fission reactions, which are much more easy to start, and that generates the energy necessary to cause the fusion reaction to happen. And so it's a very quick, explosive demonstration of fusion power. It's very uncontrolled, though, and that's, I think, why people get the issue, or are scared that, oh, fusion is uncontrollable. It's like, no, it's the nanoseconds that you have that power available. It's all going towards getting that reaction going. The second, if you were able to turn off the fission power immediately, then there wouldn't be any boom. But anyways, the NIF was started to simulate nuclear weapons testing and improve the capabilities of nuclear stewardship, which, regardless of your leanings or thoughts on nuclear weapons, this is an important facility because it means instead of having to test these bombs, we can simulate what happens with them, and that's useful, you know. But this is not designed yet for electricity generation or energy generation. The more conventional designs that aim to do this are tokamaks. Those are the ones we've had the best. And that's the donut-shaped one that has 3 sets of magnets. That's currently the best suited. There's other designs that are getting more and more traction, like mirrors, which are a giant Pringles can with a bunch of magnets going around it and squeezing the plasma at the ends to have it go together. I butchered that explanation, but just think of a big Pringles can with magnets around it. That one's really simple, and it could work really well because we've developed new magnet technology to make it work. But if you kind of look at the 1960s, we tried so many different designs, and we got that we could make very small, short pulsed reactions with inertial confinement fusion, and that tokamaks gave us the clearest path towards actual energy generation. And so a lot of the more visible, realistic companies have tokamaks as their choice. There's a few other notable startups that are doing non-traditional fusion, but I don't know too much about their designs, and it seems tricky. But yeah, I think if we're looking at making a tokamak, Commonwealth Fusion Systems is an MIT startup, and the reason why I give them as an example is because I'm more familiar with their progress. They're already put down ground and are actually building a prototype. So in 2021, they demonstrated that they doubled the strength of their magnet compared to previous superconducting magnets. And that doubling in magnetic field strength gives you a 16x increase in the power that you get out from the fusion reaction. And now, since they built that one magnet, they're going to build a prototype with 16 of those magnets. And that's supposed to finish in the next 2 to 3 years, if current timelines are followed. They have the money and the resources to do it, so they're not constrained by that. It's mainly time. And so we should get word in the next 2 to 3 years, maybe 4 years if things go wrong, word on their prototype. It should be done by them. And then once you sort of demonstrate that prototype, or it might not work, you never know. But we think, based on our current understanding, that it should demonstrate the physics we've elucidated. Then you go to making an actual commercial plant. And that's sort of what I'm focused on. Is my research is focused on developing materials that we can make that commercial plant out of. Because right now, we don't have materials to make an economically viable commercial plant. Like, the existing materials today would last for maybe 6 months, closest to the plasma, and then you'd have to wait a couple years or maybe a year if you're really, really good at handling radioactive material, and then swap out the reactor. So you'd have a very low capacity factor. And at that point, you might as well build actual nuclear fission. And so we need new materials to enable or to let the new advances in magnet technology shine. Because one of the other things that the new magnets let you do, they not only give you more power out, but they actually force you to build a smaller reactor. So that means you spend less money on magnets because the cost of these plants scales with the size. You could fit like 5 or 6 of these smaller reactors that MIT plans to build in ITER, the giant one that's in Europe. Just because that one uses old magnets, it needs to be big to get fusion to work. Because the bigger you make a plant, you have better confinement times. And that's more of a plasma physics argument. But to summarize, the new magnets give you more power, 16x more power roughly, and they force you to make a smaller reactor. Because the strength of the fields drops off as 1 over r. So 1 over the distance from the edge of the magnet. And so if that's about a meter for most plants, you just have to make a smaller reactor. Now, there's also other reasons why, but just simply, new magnets are way stronger, and they force a smaller reactor, so that's good for economics. The issue, though, you have more power in a smaller amount of area. And so that's harder to handle. So you're dealing with heat fluxes equivalent to reentry for the space shuttle. And, designing a material to handle that for a few years while also having to deal with neutron radiation, which is literally changing the atomic composition of your material. So you don't get the same material out as you put in. And we can't use most of the periodic table. So when I'm designing these materials, I'm only allowed to use like 6 or 7 materials that are, let's say, low activation. Stuff that if we irradiate it in a neutron environment, we could wait a few months and then take it out. Because otherwise, like if you put a nickel superalloy, which is what's used in aerospace for high temperature applications, you would have to wait over 100 years before it became less radioactive than Fukushima Daiichi in 2011 of March. So yeah, like it stays at around 300 or so millisieverts, depending on the nickel alloy, for over 100 years. And we weren't able to send robots in at that rate because they were just getting their electronics fried. Now, the other benefit is that this is contact doses, and it's a big solid part. It's not like a gas like cesium was when it was being spread all over the place. But the other, so that's sort of a practical limitation is we need to design materials that we can actually handle after you irradiate them. And they also have to work at high temperatures, resist neutron damage, high heat, and also be strong.
And yet you say 10 to 15 years.
Yeah. I mean, everything else is ready, like they've got the magnet technology. They have the good understanding of the physics. They're really pushing, and their prototype's going to be ready soon. Like we've never had this much funding before to do work. And that's been the biggest bottleneck is just the lack of funding. And so, and there's a ton of other, if we're looking at other examples of money increasing the pace of innovation, you can look at the automotive and the aerospace industries, and funny enough, the personal consumer brands. So this watch that I'm using was computationally designed. And they designed it on the time frame of the Apple Watch Ultra, most likely. I actually interned at the company that taught Apple how to do computational materials design. And this was, do you remember like the iPhone 6?
Yes, I do.
And how it bended? Yeah, so they actually solved bend gate, as they call it, they designed computationally a new aluminum alloy that was stiff enough to not be bendable when you put it in your pocket. And ever since then, Apple has used that technology to design new materials for every component that they work on. And so they're one of the, and now you're saying it's Apple, it's a consumer brand. This is a little bit different than Fusion. I mean, but like they went from 20 to 30 years for a new material to 1 to 2 years. So they compressed it by a factor of 15. Like right now, nuclear has a 60 to 50 year time frame for a new material. It depends on exactly what's, because there have been some exceptions, but we just certified Inconel 625, which has been around since I believe the 60s. So there's a lot of slow timeline. But if we can borrow some of the, part of my research is looking at what other, say, industries have done to speed up materials development. And so if we use some of the speed ups and some of the scaling that, and then there's also other companies, like there's automotive companies that are using this. There are space exploration companies that are using this technology. And they're all achieving rapid speed ups in what they're doing. And so we're now sort of in the point of fusion where it's an engineering problem. And one of the biggest constraints for engineering is your resources. And right now, our resources we have enough resources to do this in a timely manner. The actual limitation now is not the money, it's the people. And so if you're interested in being a part of this and part of Fusion, now is the time to do so, because there's tons of space openings in graduate programs. Like at MIT, the year before me, there was about 12 or 15 PhD students. My year, there were 25. The next year, there were 25 people in Fusion alone. So there's a ton of new people coming into the program. So it's exciting.
Well, I don't want to overwhelm the listener, so we'll leave it there and we'll have you back on. I will say that when you were talking about that, I was buying what you were saying, that it was realistic, but I was also getting mad at Apple, and I'm probably going to follow up with them because my most recent iPhone definitely bent. So I did not get the benefit of the alloys in whatever my most recent phone was. So I'm coming for you, Tim Cook. You lost me. You can't hear me. It's okay because I'm still recording. So I'm going to say cheers and see you out there, listeners, because we were already kind of done with the bulk of the podcast, and we will go from there. Thank you so much for listening to the Cognitive Dissidence podcast, brought to you by Cognitive Investments. If you are interested in learning more about cognitive investments, you can check us out online at cognitive.investments. That's cognitive.investments. You can also write to me directly if you want at jacob@cognitive.investments. Cheers, and we'll see you out there. The views expressed in this commentary are subject to change based on market and other conditions. This podcast may contain certain statements that may be deemed forward-looking statements. Please note that any such statements are not guarantees of any future performance, and actual results or developments may differ materially from those projected. Any projections, market outlooks, or estimates are based upon certain assumptions and should not be construed as indicative of actual events that will occur.